the derivative is defined as a rate of change of one quantity with respect to another. It always means so we always think of a derivative as a rate of change, right? So dy dx. How do we say that? This is literally how we say that. We could say the derivative of y with respect to x, or we could say the rate of change of y with respect to x. They're interchangeable, right? So derivatives always equate to rates of change. That's important when you're dealing with applications, right? We want to know rates of change of one quantity with respect to another. So f prime of x, sure, it's the derivative of f with respect to x, but we could also say it's the rate of change of f of x with respect to x, or the rate of change of f with respect to x. Y prime is the rate of change of y with respect to whatever the independent variable is, presumably x, okay? So if we have v of r represents volume as a function of radius, then what is v prime of r? Express that as a rate, please. Max, what is that as, boy, that's big. What is that as a rate? Rate of change of with respect to grid. Okay, if S of t represents position as a function of time, Tori, how would I write S prime of t as a rate? There you go. Okay, and if T of m represents average water temperature as a function of month, what is T prime of m? Respect to month. Okay, that's it. So those, as we investigate, we're going to get into some applications of this down the road a little bit, where we get very applied, right? This is the first year where you can actually do something real for the first time, really, in math. That we can start to look at some legitimate applications that aren't just hokey, that are meaningful. Okay, what about something like this then? So here we have some equation. R of V equals 5,400 over V can be used to determine the heart rate R of a person whose heart pumps 5,400 milliliters of blood per minute and V millimeters of blood per beat. Okay, so this is a medical application of some differential calculus here, pretty straightforward. Find the rate of change of heart rate with respect to V, the output per beat. Now let's think about this. If this person is pumping a fixed amount of blood per minute, that's not changing, that's being held constant, and V represents the volume per beat, what do you think is going to happen here? What is the rate of change of heart rate with respect to volume per beat going to look like? Is it going to be constant? As the volume per beat increases, what should you expect the output to do? If the total volume that's being pumped per minute is staying constant. If you're pumping more per beat, what's going to happen to the number of beats per minute? It's going to decrease a little bit, isn't it, right? Because now you're getting more blood per beat, so you don't need as many beats per minute to pump that 5,400 milliliters of blood, right? We see that up here. There's a graph of R as a function of V, okay? If I differentiate this, we want to come up with that function, right? The function that relates the heart rate to volume per beat. Okay, how would I do that? I just have to do a little calculus, right? So what derivative rule could we apply? We've only got one. So which one is it? It's got to be the power rule, but I have to rewrite that thing in a way where I can use the power rule. Okay? So what do you think? Liliana, can you think of a way to write that so it looks like C X, or in this case, V to the N? I can't have that. I have to have, remember, it has to look like this. My power rule says the derivative with respect to X of C X to the N equals Cn X to the N minus 1. Or in this case, the derivative with respect to V of C V to the N is what I'd have to have, right? Okay. So that makes sense. So I'm going to have 5400 V to the negative 1. That looks right, doesn't it? Okay, so if I apply my derivative rule, what's that going to give me? To the negative 2. So I'm going to get negative 5400 V to the negative 2 means over V squared. Okay? So now we could use this. We could say if we want to, it says find the heart rate at V equals 60 milliliters. Okay, well that's just a straight application of the function. I'm just really, what am I calculating here? How would I find that answer for part B? I want to find the heart rate, which is R. Yeah, that's just R of 60. Okay, good. Find the rate of change. Okay, now we're talking derivative. Immediately we know we're talking about a derivative. Find the rate of change at V equals 60. So how am I going to find that one? Yeah, that's R prime of 60. And if I plug 60 into that function, I'm just going to get something like negative 1.5. Okay. Now, what's that mean? The rate of change is negative 1.5 beats per minute per milliliter. What's that mean? Yeah, okay. So my heart rate is decreasing at that moment, and this is a measure of the rate at which it's decreasing. Okay? Does that make sense? Okay? All right. Okay, how about this one? Another example. Based on data from a research group, a model for the total stopping distance of a moving car in terms of its speed is this. There's my function, S of V, right? Where S is measured in feet and V in miles per hour. The linear term 1.4 V models the distance the car travels during the time the driver, like reaction time. And then the other term represents the car's ability to decelerate from a certain speed. Okay. Okay, so first of all, find the derivative, ds dv. Let's just find that function. So what is ds dv? (1.4). There's my first term, right? The derivative of 1.4 v is 1.4 plus 0.108, so I'm going to multiply 2 times that decimal, v to the 1, yeah, okay? And I could evaluate that at 55, and I get that answer. If I evaluate that at 75, I get that answer. Okay, so now let's try to interpret this a little bit. This is kind of a general way of interpreting this, but let's just have a brief discussion about how valid this really is. So interpret the derivative. What's that mean? Let's just kind of go through these. Well, you guys look at them for a second and tell me, what do you think? A, B, C, or D? Vote with your fingers. 1 for A, 2 for B, etc. Okay. Man, we're all over the board here. We're gonna go through it. Yeah. I'm just curious. So, so here's the problem, right? It's telling us stopping distance as a function of velocity is the function, right? Maybe that helps to be able to see that. I'm just curious. Anybody want? So put your numbers up. Okay. Man, this row was awesome. You guys got it. It's 2, but how come? Let's talk about it. Let's look at all these options here. The derivative represents the distance traveled by the car in feet for a velocity in miles per hour. No, that's the function, right? That's the function's job. You see that? Right? For the function, we're inputting a speed. V stands for speed, right? And it's calculating a stopping distance. So that's not the derivative's job, that's the function's job. What about C? The derivative represents the total time needed for the car to completely stop. No, that doesn't make sense, right? Think about what the derivative function is doing and think in terms of units. It's always helpful to think in terms of units. What would the units be for the derivative? Well, we've got units of speed divided by, or units of stopping distance divided by units of speed. So that's going to be feet per miles per hour, right? Those are not units of time, right? So we can cross out C. The units don't match up at all, which means the quantities don't match up. The derivative represents the deceleration of the car after the driver applies the brakes. I could see why people might pick 4 there. I could see why it's not the answer, but I can see why people would have maybe chosen that. Does that really apply? Do the units work out there? Deceleration of the car, you guys aren't in physics, but deceleration just means a negative acceleration, right? So if we're measuring speed in miles per hour, then acceleration or deceleration would be measured in terms of miles per hour, or miles per hour squared. So doesn't fit. Why is it B? The derivative represents the additional number of feet needed to stop a car for a 1 mile per hour increase. Well, let's look at this in terms of a graph, how about? I think this will help. By the way, there is a little problem with that interpretation. It's not bad, but see if you can tell me why that doesn't exactly fit perfectly either. So let's take this function, and I'm just going to graph it in Desmos. You're starting to appreciate, I bet, how important it is to think in terms of graphs. That is a really powerful thing to do. There's 3 ways you can always look at any function. You can look at it in terms of, algebraically. You can look at it in terms of a function, or you can look at it in sort of numerically, right? Numerically doesn't often help. Algebraically is going to be better and better for you as you get more intuition about math. But looking at a function is huge. It gives you a really strong way to visualize the relationship between the 2 variables, the input and the output variable. So here we've got S of t equals or S of V, sorry. S of V equals 1.4 V plus 0.054 V squared. Okay, so there's my graph. Now I could type in, I could graph the derivative function, but I'll show you, look what else I could do here. This is kind of cool. I'm just going to call this D of V. Okay. Look what Desmos will do. That's equal to, watch this, S prime of V. How about that? That's pretty cool. It graphs the derivative if I just tell it to, It'll calculate, it doesn't calculate the derivative function, but it calculates what the graph of the derivative function would look like, right? Okay, so let's think about this then. If we came up with, let's pick a specific value like 55, which means I'm going to have to zoom out a little bit here. If I pick a value like 55, if I input that into my function, let's get a point. Let's come up with the equation of the tangent line, right? So S of 55 equals 240.35. Okay, if I want to graph that point, 55 S of 55, I got to zoom out a ways to see that, but there it is, right? There's that point on the graph. Okay, so what are the ingredients? I don't have to make this fancy. I just need to come up with a line with the equation of the tangent line. Let's just leave it in point slope form. So that's going to be y minus the y value of that point, which is just, how could I say that without having to put a decimal in? S of 55. So y minus S of 55 equals my slope. Well, what's my slope? The derivative, which I called d, right? I can probably even do this. Let me try, I've never tried this. S prime of 55, okay, it's doing it. Right, there's my slope, times x minus what? 55, right? X minus 55, and there's my tangent line. Look at that. Okay, so there's my tangent line. Let's focus on this tangent line for a second here. Okay, and let's go, I want to go by ones. So I'm going to change, I'm going to go up here to the graph settings, and I'm going to make the steps 1, and I'm not going to show minor grid lines. Okay, that's helpful. There's the tangent to the curve, right? Okay, so what's this really saying? If I find, let's find the value of this function, of the tangent line function at 56. Okay. So I think I can do this. What if I call this f of v equals, and then I'm just going to put in point slope form here, right? So it's going to be s prime. You see what I'm doing here? I'm just trying to come up with a function for that tangent line. So I'm really just, all I'm doing is I'm solving for y. Oops, I don't want to do that. Yeah, I want s prime of 55, right? I'm just going to solve for y is all I'm doing, okay? Oh, and that should have been, by the way, that should have been s, not x, right? Oh, and then it blows up. How come? Oh, because I put it in terms of y. Yeah, so, gosh, that's kind of a pain. So I had to make that an x. Okay. So I'm going to call this f of x equals whatever that number is, s prime of 55 times the quantity x minus 55. And then I just have to add this term to the other side. And now I've got a function there. Everybody see that? All I'm doing is just solving for y, but calling it f of x. If you don't follow all this, it's not that critical. Okay, there's my line. Now I can put in the point 56 miles per hour, right? That's what that is, comma, f of 56. And there's that point. And it gives me coordinates. Just lost my little doohickey here. Let me see where that fell. Okay, so then what is this saying here? Think about this. This says that the rate of change of stopping distance with respect to velocity is given by this line, right? At 55. Think about those units. The units are feet per miles per hour. So if I increase my speed from 55 to 56, what is this tangent line predicting the stopping distance should be? Isn't it predicting here? It's saying that the tangent line is telling me that if I increase the the speed by 1, the stopping distance, the predicted stopping distance, should increase to 247.69, right? Okay, does that make sense? Because what are the units of this? Rise over run. I need to take a picture of this thing. It's not, but we're going to compare that to the function. And there's a real subtle difference between what this answer is and what's really happening. I want you guys to appreciate this. Okay, so let's take a picture. Okay, so if I made a slope triangle out of this, what am I going to get? And this is the slope of the tangent line, right? So the rise, and remember our units are feet per miles per hour, right? Those are the units of slope. And so the rise is measuring feet, change in feet, right? So that's going to be something like, it looks like it's about 7.24, right? Feet is the rise. What's the run? The run is 56 miles per hour minus 55 miles per hour is 1 mile per hour. So I ask you, what is that slope of that tangent line predicting? If I increase my speed by 1 mile per hour, what am I doing? The stopping distance should increase by 7.24 feet. Okay, well, that 7.24, that ought to look familiar. 7.24, I guess I added wrong. 7.34. You guys probably saw that and were laughing at me. Yeah, I would too. Yeah, that is a 3/4, isn't it? Whoops. Okay, right. So one interpretation of this then is the derivative represents the additional number of feet needed to stop if I increase my speed by 1 mile per hour. Okay. Marie saw something here, though, that she didn't like, and I'm with her on this. If I go back to the graph, and let's go ahead and zoom out again. Okay, so there's, oh, I need to change colors, don't I? Let's make this original function green, how about? So is the red tangent line actually equal to the function? No, it's not, right? It's not. But locally speaking, it works pretty well, right? This is called a local model, like a linear model. So all we've done is we've linearized, we'll call it this in the future. We've linearized this function to make it easier to make predictions about. Rather than having some complicated function, if I don't move very far away from my point of tangency, the tangent line acts like the function, right? If I move far away from the tangent line or from the point of tangency, the tangent line is going to deviate from the curve by enough that it's not a good predictor anymore. But if I stay close to home, yeah, the function looks pretty linear when I zoom in to that level. Yes. Yeah. So let's do that. Let's plot S of 56 and let's see what we actually get. So if we plot the point 56, S of 56, and label it, well, there it is. It's off by a little bit, isn't it? Instead of what actually would happen is we'd end up with a stopping distance of 247.744, not 247.69. So it's off by a tiny bit, but that's a good estimate of what that derivative represents. Does that make sense? Okay, give me thumbs on that. Is that, you see why we can kind of, as a rule of thumb, we can say, okay, if we increase the input quantity by 1, the derivative is telling us what the predicted change in the output quantity would be. Okay. Now, that wouldn't be such a great way to do it, though, like in this last, oh, if I go back a little bit, like down here, right here, average water temperature as a function of month. Well, we might be taking some pretty big jumps in water temperature from month to month, right? That's a pretty big increment in my input values. So is that, the derivative interpretation we were just talking about may not work so well there, right? T prime of n would really sort of predict, if I move to the next month, what should the increase in the water temperature be? Well, that may be too far for our linearization model. It may be such a big, the function may have deviated from its tangent line too much for us to really use that interpretation there. Okay. Uh, no, it's not. It's simpler. All we're saying here, and people sometimes like get real, they want to make this out to be something that's harder than it is. Like if I go back, let me go back here, and you can see here, again, you can see that the linear model is good locally, but it's not perfect. But as long as we're staying to where the linear model is pretty accurate, this is not a bad way to approximate a function, is using a line, using the tangent line. Oh, you guys aren't seeing that. Whoops. Forget, right? So there's our function. Again, you can see here, especially if I let me compress this vertical axis a little bit. Like if I make this go from, where are we at there? Like 200 to 300, how about? That didn't help at all. Never mind. I, I didn't help at all, but you get the idea, right? I don't know what I was thinking there. That this is much simpler than linear regression. All this is doing is literally just creating the equation of the tangent to a curve at the point of tangency and using that as a model, as a local model, because it's easier to manipulate a line than it is some complicated curve. Okay. All right. Moving on here then. So this is why, and have you ever had this experience? You're blowing up a balloon for a child's birthday or something, and initially that's pretty satisfying, right? You start blowing on that balloon and it just gets really big really fast. But after a while, it starts to lose its luster, because what happens? After a while, you're blowing like crazy into this balloon and it's hardly even getting any bigger, right? How come? Well, that has to do with the derivative, right? If we look at this example, in Desmos. So here's V of R. There's velocity as a function of R. Now we can't have negative radius of a balloon, so we'll just look at it from 0, right? So as the radius increases, the volume of the balloon increases at an increasing rate, right? If I look at the derivative of this, there's the derivative function, right? The value of the derivative increases pretty rapidly as R increases, right? If I have a really big balloon, and just think about this in terms of, like, if I have a small balloon that's got a radius of like 1 or something, and I'm going to put 10 cubic units of air, like say it's 1 centimeters the radius. If I put 10 cubic centimeters of air into that thing, well, man, that's massively increasing the radius, isn't it? That little bit of volume. That 10 centimeters goes a long ways. But if I have a balloon with a radius of 1,000 centimeters, which means that the volume is over 1 million, right? Like over 3 million cubic centimeters, adding 10 cubic centimeters, that does almost nothing, right? That impacts the total radius barely at all. Okay, so this picture really tells you why that's so initially satisfying, but eventually not at all. Now, this is the wrong way to write the derivative, though. What I've graphed here is dv dr. What I really would like to do is graph dr dv, wouldn't I? The rate of change of the radius with respect to volume. So as I put volume into the balloon, how is the radius changing? All I have to do is just invert that derivative, or I could solve for r. If I solve for r, I just get this function. That's better, right? Look at that function. That's radius as a function of volume, right? After a while, if I graph that derivative, look what happens here. That derivative, man, that's getting really small after a while. Clear out here, a small increase or an increase in volume does barely anything to the radius. In here, an increase in volume does a lot to the radius, right? See how the rates really describe that way better than just the equation does? Okay, that's good for today.